True. So we will see whether we think the same thing or not. That will be interesting. So what I want to do is, I mean, I don't know you, I don't know what you know, what you don't, what you like. And so I have chosen a kind of very waving hands presentation, not very technical. So if you know a lot about that, maybe you will be disappointed. I hope not too much. So please feel free to interrupt if you think that something is missing, some you need explanations, or if I can skip and very quick, just let me know. Okay. So yeah, I wanted to talk about semi-classical analysis, and I begin with a kind of pictures of what is of the story of semi-classical analysis in France, maybe. You see the first sentences in French. And the town here is Nantes in the 1970. You can see it with the cars, which are very old-fashioned, I think. And in fact, it's at that time that people in France get interested into what they call semi-classical analysis in the mathematical community. So the sentence there is from Bernard Helfer. He wrote a text about semi-classical analysis, 40 years of semi-classical analysis. It was in the beginning of this century. Yeah, and he says that semi-classical analysis means studying the correspondence principle, and the idea is that one should find a trace of classical mechanics from quantum mechanics when you pass to the limit the Planck constant to go to zero. Okay, so this is the idea. The idea is to connect classical mechanics.
Clotilde, the screen, the sharing of screen is deactivated for some reason.
Ah, sorry. Okay. So I've made something stupid, but what? Yeah. So you don't have the pictures. Yeah, it's better.
Yeah. Yes. That's fine.
Okay. So you have to open the chat to see it because. Or you just you check the chat. Yeah.
Yes.
Okay, perfect. So I don't think about it. And yeah, I wanted the page before. Yeah. Okay. So here it's Nantes, and here it's Bernard Helfer, who is one of the people who have spoken a lot about semi-classical analysis. And I have taken the sentence from his one of his paper, and Johannes Rostrand that you may know. And in fact, these people in the 70s, they were people who were trained in microlocal analysis. We will go back to that later. You see microlocal analysis, and they decided they want to invest what they have learned in the mathematical framework to mathematical physics. So it's a kind of concern from mathematicians who goes to mathematical physics, who wants to say something about physics. And it's in some sense it's a funny thing because in fact this microlocal analysis, which is a mathematical theory developed for PDEs, we will talk about it later. In fact, it was appeared and it was motivated by quantum physics. So in fact, you have a kind of way back and forth. People, mathematicians were taking techniques from quantum physics for doing mathematics, analysis of PDEs. And then these guys who are very trained to that thing, they want to go back to physics. So you see a kind of movement forth and back. And the story in France begins in the 70s, as I said, with, so I have put a couple of numbers there, and there is, for example, Didier Robert, Frédéric Pham, and Bernard Helfer. So they were in Nantes, and they were working with Rostrand and Cesarin on some kind of ANR program. It was before the French ANR. The French ANR was existing, but they had some finance support to do something about semi-classical analysis and interactions between interdisciplinary work between physics and math. And what is funny is that they are writing exactly the same thing that we say now when we want to write some proposal for interdisciplinary work. We begin by explaining that we want construct a common vocabulary to be able to discuss together. And then in their applications, they were doing the same. So this is the story that Bernard is telling. Exactly the same thing that we say, okay, we are still saying 50 years after. Yeah. And so what Bernard Helfer says in his presentation of his story is that the first work, in fact, is André Voros' thesis from 1977. André Voros was working in the CEA. In fact, it's some kind of CEA is the Agency for Atomic Studies. So you see a mathematician who was in contact with physicists. Okay, and then I have added some names in my slide. Jeff Roche, who is in the US. Okay, Victor Ivry in Russia. It was the SSSR at the time. Okay, so you see this kind of picture. Who were very pioneering people in semi-classical analysis, and there were no women. So I have added Monique Montesquieu. We will come back to her later. Who was with, I think she's a little older than Didier Robert, and have been working together a lot. And Gerd Grube, who is somewhere. Where is she? She's somewhere like, I don't see her. Yeah, here, Gerd Grube, who is a Danish woman, who has worked a lot in microlocal analysis, maybe not so much in semi-classical context, but yeah, I mean, she was the only woman of this generation of Ormander and all these kind of people. So we will come back to that later. So in fact, my talk will be organized more or less like that. I will discuss first what is a semi-classical problem, mainly by showing some problems that people consider usually like semi-classic. And I will discuss a little bit about the correspondence principle, and give two applications of, okay, there is this kind of metaphysic idea to observe a shadow of a classic when you go to quantic. You see, or I don't know, or to find the shadow of quantic world when you look to classical mechanics. It's something like that. It's kind of, which is quite large. And in fact, there are applications which are really interesting for numerical purpose, for example, so that you can, if you have understood more or less this kind of a paradigm, then you can do real work for computing things, for example. And then if I have time, I will open some other problems which are more I mean, which are more today problem than, I will talk a little bit of old problems, or maybe not so old, but a little bit. Okay, so some semi-classical problems. So maybe the main one, the one in which the first one I learned in my thesis, you were speaking about my thesis. So semi-classical PD is the Schrödinger equation. Yeah. So this Schrödinger equation, which is written here, I epsilon dt psi equal minus epsilon square over 2 Laplace psi plus v psi. Okay, so it's, of course, it's in L2. The initial data is a square integrable function, and you have a parameter epsilon here before the Laplace. You see the little arrow, the pointer. Vous voyez? Yeah. Okay. And this parameter is small. So in fact, the problem is semi-classical if there is a small parameter. So as you see before, I mean, the paradigm is to say what we should see the classical mechanics by letting the Planck constant go to 0. Here I have no h bar. Yeah, so I have some epsilon, which is not related with h bar, but is related with physical quantities in the frame of Born-Oppenheimer approximation. So Born-Oppenheimer approximation is the kind of framework which has been given in the 1930s, and it's a way to simplify your equation, your Schrödinger equation for describing the dynamics of a molecule. There are too much parameters, and there are methods developed by Born and Oppenheimer to reduce the system to have less variables. Okay, if you think to a big molecule, 3 parameters per atoms, it gives something very, very weird, and then you manage to write. There is one way to reduce the number of variables, which is what is called Born-Oppenheimer approximation, and you are left with some some equation which is scalar if a potential is scalar, but you can also consider it like matrix valued with a matrix psi epsilon, which could be a vector. But for the moment, just stick to a scalar background. And this epsilon now is small just because it's the square root of the ratio of the mass of the electrons divided by the average mass of the nuclei. Okay, so in Born-Oppenheimer approximation, the idea is to think that the nuclei are very heavy, so they don't move so far, and the electrons remain quantic. And so you can reduce the problem by using this kind of scaling. So there is someone which is very small, in fact, and for good reasons. We don't let it, letting the Planck constant goes to 0, it looks a bit naive. But here we can say that, okay, we have a model with a small parameter, and we want to compute quantities to say something about our system. In the limit, epsilon goes to 0. We want to have a first order, second order, third order. You see, it's something that we call asymptotic analysis. Okay, so the question 1 in this frame, the question is to say something. Most of you are physicists, so you know that the wave function itself doesn't mean a lot. But what is interesting is the density of probability of presence. So what we want to know is to compute the integral on the set A of psi epsilon square dx, just to know this will give a probability of finding the molecule at the position X in the set A. Okay, so it's a density in position, and it's these quantities that are interesting, in fact, that one can want to compute. So this is the first type of problems where there is a kind of small parameter which appears naturally. Okay. And another problem, which is maybe closer to your preoccupation, Simon. So a spectral problem. You take a compact Riemannian manifold M, so a torus, for example. You look to the Laplace operator on this manifold, and you look to the spectral problem. So since your manifold is compact, it turns out that there is a sequence of eigenfunctions and eigenvalues, and the eigenvalues lambda n, they goes to 0. So what is it's an old problem to study how the density of the wave functions is concentrating on the space. You see, you just think, okay, it's not waves, it's the Laplace operator, but in some sense it's related with the frequency of oscillations of waves. And you want to know, you take this Chladni experiment when you have something with a plaque which moves and there is sound on it. And when you increase the frequency of the movement, then there are some nice pictures which appear on the plaque. And the form of this picture is related with this density, in fact. Okay, roughly speaking. Yeah, and so this problem a priori is not semi-classical, but a lot of results have been obtained by thinking to it as a semi-classical problem. So the idea is just to say, okay, lambda n goes to plus infinity. I'm interested in this sequence with n going to plus infinity. So there is someone small, which is 1 over lambda n. You take the square root and you put the lambda n was there, you put it here. And now you have something which is rather like, which looks like the Laplace there, which is scaled. In fact, there is an epsilon square just before the Laplace. So this problem has been considered as a semi-classical problem, and then with semi-classical techniques, it has been possible to give elements of answers to these questions. How are these densities? Okay, sorry, it's in French. Report. The idea is to say something about the density of eigenfunctions. Okay, so we see there is asymptotic analysis, which is behind very, very. If these semi-classical techniques have been studied, it's because they allow to give a nice asymptotic analysis of problems which are of physical interest. And I have also written the word high frequency analysis. Because high frequency, you see the frequency is the lambda n of my eigenvalue problem, is the frequency of my system, and we are looking to large lambda n. So it means that 1/λn is small, but the high frequency analysis means that we are looking to solutions that are highly oscillating. Okay, just think that if epsilon square Laplace of a function is bounded, for example, is something like exponential I x over epsilon. So it means that it's oscillating a lot. And this is one of the difficulty of this problem, is that these solutions are highly oscillating, so it's difficult to mimic them numerically because you need very tiny grids. And the more epsilon is small, the more you need a fine grids. Yeah, so just thinking to high frequency analysis, it means that these techniques have also been used when you have a problem without epsilon. For example, you take the Schrödinger equation, which is on this side, and you take epsilon equal 1. You know, so you have an equation I dt psi equal -1/2 Laplace psi plus v psi. Okay, so it's just a Schrödinger equation. You want to say something, but you want to say something for data that are oscillating. And then you can think to this problem like a semi-classical problem, because you have a small parameter which is given by the data. So the data is sometimes the semi-classical parameter is not in the equation, but in the data. You have data which are highly oscillating, and then you want to study these equations, and you can always make it more or less semi-classical just by multiplying by epsilon square. So what is important is that the position derivative are scaled with the epsilon. So what is crucial is to have epsilon square Laplace here. Then if you have epsilon square there, it just means that your potential is very small. It's not a problem. And the way you choose the time, in fact, is just a matter of choice. Your choice, you are choosing to study a large time or short time just by choosing the scaling here. Okay, so we can think to a problem, we can say that a problem is semi-classic as soon as the derivative are appearing with some small parameter. You have some epsilon dx somewhere, and then you want to know what happens when epsilon is small, and then you can say, well, it looks like a semi-classical problem. Let's try to think semi-classically. Okay. So the correspondence principle. So we go to
a question here. I don't know if we can ask along the way or
yeah. Go ahead, yeah, please.
So when we speak about semi-classical, and here we have the example of this Schrödinger equation.
Yeah.
We mean always we think about this exact equation, this form general of equations, or okay?
No. The only thing you need is that your equation has some epsilon dx. Whenever you have dx, you have epsilon with it. You see?
Okay.
So, but for example, here I could put epsilon square before the dt, or nothing. Yeah. But which makes it semi-classical is this Laplace with epsilon square. So there is a small parameter. To be semi-classical, you need a small parameter. You are doing asymptotic analysis. Okay, you want to have to let someone go to 0, and you have the epsilon square with the derivatives, and in the initial data also you need to have oscillating. Or you will say more things about data which will be oscillating with the same kind of oscillations. Yeah, it's okay.
Okay, thank you.
So, as I said before, all this semi-classical analysis is very related with microlocal analysis, and microlocal analysis, in fact, is just doing math or studying PDEs with a quantum mechanics background. You know, just thinking in the phase space instead of looking just in position, or just working in the phase space, and not only in the x variable. Yeah. So, I mean, we are going to think into the space of positions and impulsions, which is the phase space of quantum mechanics. And in terms of mathematics, it's a cotangent bundle. Okay, so if we are in RD, the phase space is just RD times RD, and we don't really need to think about it like the cotangent to RD, but in fact, all the geometric transform are transform of the cotangent of RD. And because of these geometric properties, it means that you can use the same approach on a Riemannian manifold. And that time, the phase space is the cotangent bundle of the manifold. Okay, so it's a very nice geometric background, and that's the reason why it has been. I mean, it's powerful, in fact. So, as you know, to pass from position to impulsion, you need to use the Fourier transform. So my convention is, my convention is to take the Fourier transform like up there. So I integrate f of x against exponential minus I xi. There is no pi, which explains that when I look to Fourier inverse formula, then I have to pay 2 pi minus t. So it's not an introduction, but it's okay. I have a constant, and it's here just to agree of who is who today. Yeah, and then the crucial relation to pass from the position space to the Fourier space is the relation of the Fourier transform, the behavior of Fourier transform with respect to the derivative. Now, okay, one derivative in the position space means multiplications in by xi in the impulsion space. Yeah. So sorry, what happens? Yeah. Okay. So what we are going to do, so the first thing, in fact, which is, I mean, it's the idea in quantum mechanics is to quantize the functions on the phase space. Yeah. If I quantize x, it's a multiplication by x. If I think to an operator related with psi, it will be just the derivation. And now I have a functions a of xi, which are function on the phase space, but I assume them to be smooth and compactly supported. And we are going to associate with them a semi-classical pseudo-differential operator. Okay, so this process is something that had been developed by Ormander in particular. So how we do that? In fact, we just use the inverse Fourier formula that we had before. Okay, so if I multiply f by a function a of x, okay, I can put the a of x here. And if I multiply it, for example, by if I differentiate it, it means that here I multiply by xi. Okay, minus I dxf is the integral of xi, da, da, da. Okay, so I can imagine a Fourier multiplier, and Fourier multiplier, it means that here I put a of psi, and I will get something like something that usually is written a of d. Yeah, okay. And so the idea is to do to have a kind of algebra where you can algebra of operator when all these things are as a meaning, and you can mix x and psi. So the idea is just to put at that place where I wanted to multiply the Fourier transform, I multiply by the function a of x and epsilon xi. Yeah. So why epsilon xi? Just because, as I said before, we are in a semi-classical setting. Our xi are more or less, I mean, all the derivatives are affected with an epsilon. So epsilon is going with xi. Okay. And you can also think that it's a high frequency analysis because my A is compactly supported. So it means that I have selected some range of xi for which epsilon xi is in a compact, which means that xi is xi over epsilon. Xi is like some constant over epsilon. So if you think to A that 0 is not in the support of A, so that epsilon xi is larger than something, you have exactly selected a range of momenta. Okay, so what we have done, in fact, is the microlocalization because it's local, since the x are just on the support of A, and it's microlocal because the xi is also, the epsilon xi is also localized in the compact. So you have selected in the function f, you have selected some x and some xi simultaneously, and large xi because it's epsilon xi that we have put here. Okay, so this kind of approach without the epsilon, you can do also things. Of course, you can take epsilon equal 1 in the equation, and the more elaborated pseudo-differential calculus is with functions which are not compactly supported, but which have some decay at infinity So you have these, maybe you have heard about the Ormander classes, which are a very elaborate theory of pseudo-differential operators. It's I always talk about Ormander, but I should say Peter Lax was very involved in this in the development of macrolocal analysis, and Victor Maslow in the East and in the West. So Victor Maslow, I think, is one of the Russian guy who was what the idea of these operators. Okay, so we see that in fact it's the kind of basic tool. You have this semi-classical pseudo-differential operators that allow to select some range of x and some range of psi. So you are selecting each time in position and in impulsion your function, and you can study more precisely how it behaves just by selecting things. In fact, it's the same idea than in harmonic analysis when you select frequencies. Yeah, so that's the reason why I write these words, because it's the same thing that usually is done in that setting. Okay, so in some sense, what has to be observed is that here I have made a choice. I have put x because it's the more natural, but if we think about it, I could have put y. Here is the formula. I have developed the Fourier transform, but if I put y here, and there is no dependence on psi for the function a, it means that the x is equal to y, and it doesn't change things in some sense. So there are different ways of quantizing, and there is no reason to put x here or y or anything like the half sum x plus y over 2, or more generally something which is just something in the segment xy, something like 2x plus 1 minus 2y. So one talks of a tau quantization. You take tau between 0 and 1, and here you play this little game. And even with this little game, it remains that if A is independent of psi, then you have here something which gives you the Dirac mass in y equal x, and you are left with the operator of multiplication by x. Okay. So for choosing, since we have a choice, there is one way that usually people use, is to take the tau, this is tau to 1/2, because if you take the half sum, it's perfectly symmetric in x and y. And then the operator that you construct, when A is real valued, it gives you some self-adjoint operator. So usually self-adjoint operators are good guys. So the idea, usually people take what we call via quantization, which consists in taking tau equal 1/2 here. Okay, but sometimes one just stick to that quantization, the one for tau equal 1, because it's natural also in some way. So this is called the classical quantization, and that one is the via quantization. Okay. So the point is, it's important to see why this class of operators is bounded in L2. Okay, because we are working in L2, and we want to select some kind of position and momenta domain. But I mean, we want to do that without too much drama, and in particular, we have to control the growth in epsilon. Yeah, and the point is that the family of operator of epsilon of A is bounded in L2 uniformly in epsilon. Okay, and this comes from a simple argument which uses that if you look to this operator, you see it has a kernel. In fact, it's the integral of a function of x and y, f of y dy. Yeah, and this kernel is depending on x minus y over epsilon. Okay, so in fact there is this x which is hanging around, but we are not integrating in x. So x is just a parameter, and here there is a y, but we can write everything in terms of x minus y over epsilon. Maybe it's more prominent here. No, it's not more clear. Sorry. Just take tau equal 1. It's easier. So you have no y here. You have a of x psi, and then this x minus y over epsilon, which smells convolution. In fact, we can write this operator of epsilon of A as the convolution of f with this function which is x dependent, function of y. And this function of y is just epsilon to the power minus d, and the inverse Fourier transform of A taken in epsilon minus 1 y. Okay, when I convolve, I change y into x minus y over epsilon, you see, and then I have the inverse Fourier transform, inverse because of this exponential ixi dot x minus y over epsilon, and the A, which is there. Okay, so remember, A was compactly supported, smooth, so its inverse Fourier transform is Schwartz. It's a very nice function. And it's a kind of kind of scaling in epsilon, which is preserved is the L1 norm of these functions. Okay, epsilon minus d. When I integrate in y, it's exactly what we need to say that the L1 norm in y of this function is just the L1 norm of Fourier minus 1a of x dot. Okay, and this is the thing that makes that these operators are bounded. You use Young convolution inequality. So what we want to evaluate is the L2 norm of kx epsilon convolved with f. We enter absolute values everywhere, okay? And we take the supremum in x of this function. Remember that x is in a compact, so this is doable. And then Young inequality tells you that the L2 norm of a convolution is bounded by the A1 norm of the first term times the L2 norm of the second one. So then you are left with these L1 norms of Vk. And this, it was exactly what we said, it's the epsilon disappear. So these operators are bounded in L2. They send the function f in L2 into a function f in L2, and the norm is bounded by this quantity, which is just a number because the inverse Fourier transform of A is a Schwartz class. Yeah. So it's nice operators in the sense that they are bounded from L2 into L2, and the proof is proving that they are bounded is not a real issue, in fact. Okay, so what is quantum classical correspondence? A way to see it, is to look to Egorov theorem. So it's I should have looked which to put a year, but mid 20th century, something like that, maybe 30s or 40s. I'm not so sure. Yeah. So we take our Schrödinger operator and we look to the evolution to this Smith group associated with this operator. Okay. So you need to put assumptions on V so that this operator is self-adjoint, and then you conjugate a pseudo. So here I have put I have taken Y quantization, but okay, it's not a real issue. We'll see later. Okay, and then you sandwich. We conjugate him with the evolution operator by the Schrödinger propagator, and what you find is at leading order again a pseudo-differential operator with a new symbol, and the symbol is just the A composed by the flow map, so the classical flow map associated with this Hamiltonian. Okay, so if you look to Newton equations for psi square over 2 plus V, the solution is just Q of t, P of t with Q dot equal P and P dot equal minus gradient of V. Okay, so this is the acceleration. The acceleration. No, sorry. This is the position. Yeah, I differentiate, so I find the speed, and I differentiate the speed. I have the acceleration. It's minus the force. Yeah, some des forces égale ma for those who learned it in French. Yeah. So I have my classical trajectories, which are one from the Newtonian mechanics. And in fact, when I take an observable, so my observable are just this function A, I quantize it with the Y quantizations. I conjugate it with a propagator. And what I find, I think, the order is just the A composed by the classical transport. Okay, so we have linked quantum evolution with classical transport. Egorov. Yeah, and the remainder is rather good. It's epsilon square. if I had not taken the y quantizations, I would have the same result, but with only epsilon. Yeah, but it's not so bad. Okay, so of course there are some time issues. You see, t as to t epsilon t. You should go to long times, but not too long. I mean, log of epsilon is enough. Is still possible, but not too long times. It depends, in fact, on the flow. So here it's a very rough result, assuming that v is subquadratic, something like that. But for some systems, this kind of asymptotics can be ameliorated on long time. So what are questions that people discuss now, in fact. What people want to understand is how long this kind of approximation is true for different systems. This is a range of questions. Okay, so this is, yeah, so the idea in the following, I said, is to show you that, okay, this is a kind of quantum classical correspondence. Now we want to use it for answering to some of the problems I had settled before. And my first application will be to discuss how evolves the expectation value of observables. So what do I call expectation values of observables? Is quantities of that form. So you take a semi-classical pseudo-differential operators of epsilon of A, and you apply it to psi epsilon, and now you want to describe the evolutions of these quantities. Okay, so you remember that we wanted to say something about the densities of the limits of psi epsilon of tx squared as a measure of dx, the integral over A of psi epsilon of tx squared dx. Okay, so here we have so if my set A, where I want to compute this density, is bounded, okay, I can say that I take a function A, which is smooth and is covering this set, okay. But here, when I take a pseudo-differential calculus, I am also cutting the frequencies. Yeah, I am looking to the psi, which such that psi epsilon psi is in the support of A. So it means that if psi epsilon, we need to connect these expectation values to the standard position densities. You need to know that your functions is not oscillating, has no oscillation larger than 1 over epsilon. So you need, with some precautions about psi epsilon 0, if the initial data is more or less what we call epsilon oscillating, meaning that our oscillations are not larger than 1 over epsilon, then you can connect the densities that I was describing at the beginning and these expectation values of observables. So that's the reason why we are not losing so much, in fact. So it's the solution of our Schrödinger equation, psi epsilon, and now we want to describe these things when T evolve. Okay, so usually, I don't know, it depends on communities, if I can say, but usually these quantities are written as in terms of Wigner transform. I mean, if I write the equation, I can write what is this quantity. It's a big integral in x, in y, and psi, if I think to the variables we had before for defining the pseudo. But you can make change of variables and write it like an integral over R2D of A times some 1. And this is the Wigner transform. The Wigner transform, it's written here with quantities, is just the functions which is acting as a distribution on the class of on the observables A. Okay, so it depends on context. Sometimes people prefer to think Wigner transform, and sometimes people think pseudo-differential operators, but more or less the connection is really direct. Okay, and if so now that I know that I have this connection, I have defined my Wigner transform, I can wonder how is the Wigner transform at time t. At leading order, I use the Egorov theorem. So my psi epsilon of t is exactly the exponential minus it over epsilon times the operator h applied to psi epsilon 0. It's the propagation propagation of psi epsilon 0 by the Schrödinger evolution. Okay, so when I compute these quantities, I have my sandwich, and so I apply Egorov theorem, and it's the epsilon, the pseudo-differential operator of symbols A composed by the flow applied to psi epsilon 0. Okay, and if you know the initial data, it means that you can say something at time t. Yeah, so you have a kind of relation at the level of the Wigner transform, which tells you that the Wigner transform propagates along the flow. You see, so it's interesting because in the flow I have no epsilon. It's just ordinary differential equations. While these quantities W epsilon F, they were highly oscillating. You see, you have exponential I over epsilon, ta-da-da. So it means that if I know this quantity, the Wigner transform of the data, I can compute a good approximation of the Wigner transform at time t. Okay, and this suggests some kind of numerical realizations for computing the Wigner transform, which is in fact more convenient than solving the equation and computing the wave function at time t. Okay, so then the basic point is to be able to describe the Wigner transform at time 0. Okay, so we think here we have this the Wigner transform of psi epsilon 0 at time 0 is given by a big integral on RD. Okay, this integral is highly oscillating, so it's a shitty game. Yeah, so there are methods for that, like Monte Carlo and so on. So if you are able to replace your initial initial Wigner transform by sampling with weighted points, so the ZG are points and the WJ are weights. Okay, meaning that if I want to compute A times the initial Wigner transform, I just sum the mass WG times A of ZG. Okay, but now that you have your weighted points, all the dirty business is done because you just need to propagate them along the trajectories. So there is a H here that should not be there, but yeah, that's it. It's the flow. You construct the trajectories which are leaving these flows, and when you sum up at finite time with the same weights and the new points generated by the trajectory, then you obtain a good approximation of the Wigner transform. And in fact, all the dirty business that you have to do if you want to solve the equation here with a numerical solver, thinking that D can be larger, then you have this here. It's more difficult because there is this epsilon before the dt, the epsilon square here, and then epsilon is smaller, so it creates a lot of trouble. All the trouble has been put on the sampling of the initial Wigner transform. Okay, so this kind of methods have been developed by Caroline Lasserre in Munich, and in fact, it's really a nice method just because there are solvers for solving ODEs. In fact, these ODEs, there are some structure. I told you that the phase space is a cotangent space. So these ODEs, there are Hamiltonian trajectories. So there are some kind of there is an elaborate way to treat these ODEs, and it's very efficient. It gives efficient algorithm. And then just to say it, then you can play with the epsilon square and trying to ameliorate the estimate by a tiny modification of the flow map. I think she has written something like that too. Okay, so you see that this kind of metaphysical idea of at the beginning, which was just to show to link quantum mechanics and classical mechanics, in fact, it has real consequences, because you can, instead of solving the quantum problem, which is complicated, because you have delimited what you want to know, just to know the Wigner transform, which is, meaning that you just want to know quadratic quantities of the wave function. Then you have a method which is just using ODEs. you are just solving ODEs, while before you had the PDEs. Okay. Any question? No? Good. So maybe I switch that one. And we go to the wave function. So I said, as I said before, when we look to this first kind of looking to expectation values, we do not see the phase estimate of the wave function. Yeah. And just to illustrate the correspondence quantum classic, there is another type of functions which are interesting, which are the coherent states. So these coherent states they have been introduced in the 80s by Monique Montesquieu, Didier Robert, and Georges Godon, separately and somehow differently. And it's a game with the uncertainty principle. So the uncertainty principle tells you that you cannot know the position and the momentum of a particle at the same moment. Okay, or usually it's expressed as dx dxi. So the uncertainty is smaller than h bar, and for us, more or less, h bar equal epsilon. Yeah. So what we are going to consider is special data which are bounded in L2 that we call wave packets. So these wave packets, they are very localized close to a point x naught, and in fact they are micro-localized, close to a point x naught psi naught in R2D. Okay. So how we see this? So they have a profile, this function which is Schwarz class, and you compute phi of x minus x naught over square root of epsilon, meaning that it's very peaked. Okay, the function is very peaked, and it oscillates here with a phase I x psi 0 over epsilon. So it's oscillating like 1 over epsilon psi naught, close to x naught. Okay. And here it's just the L2 scaling to get the L2 norm of this thing is just the L2 norm of phi. Okay, so it's a nice if the norm of phi is 1, it's just a wave function. Okay, which is very peaked. So the fact that it's very peaked, there is too much phi here, is you can see it, for example, if you take the Fourier transform of this thing. If you compute it in psi over epsilon, then you get a wave packet. The point has changed. It's psi 0 minus x 0. Okay, kind of. And the profile is now the Fourier transform of phi. Okay, so in position, it's peaked above x naught, and in momentum, it's peaked above psi naught. Okay, so very localized wave packets. And maybe we forget 2 because it's not very important. What is interesting is that when they evolve through the subgroup of the Schrödinger equation, yeah, it remains, they keep at leading order this structure of wave packet. So if we look to the action of the unitary propagator time on these wave packets, we have first the phases with function s of t, which is the action, and the formula is in the next slide. Okay, and then you have a wave packet which is exactly located above the point where the classical trajectories has arrived, phi t x naught psi 0. So you have the x naught x 0 psi 0. You take the classical trajectories, you look up to the time t, and then your wave packet is just above that point with a profile which is obtained from phi just by solving Schrödinger equation with harmonic potential. So you have the Hessian of v xx phi of t. Okay, so it's time dependent harmonic oscillator. Okay, you see here it's a matrix, so it's the Hessian of v along the trajectory. Okay, and it gives some kind of harmonic potential. Time dependent, you can. That's the way to compute the profile phi of t. Okay, but these equations, they have very nice solution when phi of 0 is a Gaussian. So if you start from a phi which is Gaussian, in fact you remain Gaussian. So the result is for Gaussian. So I have the notations for the Gaussians. If I start from a Gaussian, it's remain a Gaussian. So a little more about Gaussians. So we consider a large class of Gaussians, not only exponential minus x squared over 2. Okay, here you see there is a matrix gamma, and this matrix gamma is complex valued, but its imaginary part is strictly positive, so that this is the Schwarz function. Yeah, it's norm 1, and there is some, it's symmetric, and there is also some, so it means that here there is some oscillation that are more or less involved. Okay, and then you construct a Gaussian wave packet, which is you take the process we have described before. Sorry, and we choose a point QP of a phase space, and we take the Gaussian wave packet associated with this profile G0 gamma and at the point QP. Okay. So when, for example, to find the standard Gaussian, you just take gamma equal I identity, and then you have this the standard normalized Gaussian. Okay, with a 1 alpha it would be better. Yeah, and the interesting thing that people have used is that you can decompose a function as on the Gaussian frame. Yeah, so if I take the scalar product of G epsilon Z and F, so this is just the L2 scalar product, so this is depending on Z only. I integrate against G epsilon of Z of X, I integrate in Z, okay? So I get a function in X, and these functions turn out to be exactly F. It's just a game with Fourier transform, yeah? But this is very funny because you think, okay, now I want to know the evolution of F of X, yeah? Through the Schrödinger propagator. So I apply my Schrödinger propagator to F. It passes through the integral. This is a number. It's the wave packet. The wave packet here, and we know how a wave packet is evolving. Okay, so we can write kind of approximation of the propagator just by putting, so we take the propagator, you enter it into the integral. It is now acting on the wave packet, and then you replace your wave packet by the evolution with the action and the new profile, which turned out to be still Gaussian, but now with a variance which has moved. Okay, so there is here a big matrix gamma of Tz that can be computed, and now you have a kind of nice formula for computing the leading order term of your approximation. Okay, so these things have been introduced by a theoretical chemist, in fact, not by a mathematician. And it was Kay, I think, in 2006, who was the first one to use this kind of approximations for approximating the evolution of the propagator of the Schrödinger equation. Yeah. So of course, I mean, it's not so direct because you have remainders and you have to treat the remainders. So when you are mathematicians, you want to have an approximation in L2, something like that. And this has been done later by Roos and Swart and by Rover. So 3 years after, 3, 4. Yeah. Okay. And when you are left with something like that, in fact, you can, you see in the integral, all the quantities which arrive in the integral are just linked with classical trajectories, classical action, and this is what I call the taught variance. So taught because it moves, you see. So it's not the same. Here I have I identity as a variance, and here I have this matrix gamma, which is a little weird. And for computing it, it's again solving ODE. So you take the flow, you differentiate the flow. You have a Jacobian of the flow. This is this big matrix F of Tz. It's a 2D by 2D matrix, so it has 4 blocks. And then you play a game with the blocks, and it turns out that this is the gamma. Okay, so it's very explicit in some sense, and very and very, I mean, just ODEs again. But if you know the V, you can compute these things. Not sure. Oops, sorry. Well, rather more or less easily. Okay. And so just to mention it, in fact, what the physicists again, Kay and the other guys have proved is that you can go back to standard Gaussians. So it's frozen Gaussians because now the variance is not depending on the time. And pay instead you put the coefficients there. So there is a new approximation, frozen Gaussian, which is called like that in the chemical literature. When you have replaced the moving variance by a coefficients, what we could call a Hermann-Klug prefactor, because there are results of Hermann and Klug on the same direction. And here again, the U can be computed just by playing around with these coefficients of the Jacobian of the fluid. Okay. But what I wanted to say, and I will conclude with that, is that you can, again, these kinds of approximations open the door to numerical realizations. Okay. So now the tricky part is to have a kind of sampling of data. Okay. Now you want to that your initial wave packet is replaced by a set of points, the sum on Gaussians. Okay, so you replace your Bargmann approximation by a sum of weighted points. You propagate your weighted points. You compute all the associated quantities, and then you have a kind of descriptions of wave functions at time t. Okay. So for the word of conclusion. Yeah, systems maybe I switch, I go to the conclusion, I think it's here. So there is a big issues about systems, because when you look to what you really need, for example, the system that the theoretical chemists are using, the Schrödinger equation is matrix valued. So the V has eigenvalues. So there are coupling between you have several Schrödinger equations, but they are coupled through the potential. And in fact, it's okay, there are new issues, and this is something on which we are working. And then you can go think to the geometric questions that we add with this eigenvalues of a Laplacian on manifold. Okay, and in fact. This semi-classical setting, it can be transferred to Riemannian manifolds, but it can also be transferred to more general context, okay, non-commutative one on some Lie groups, and to study sub-Laplacian operators, or what is called Rockland operators. Yeah, but maybe I will not say too much unless you have questions. But yeah, okay, there are still developments of semi-classical analysis in new contexts, in non-commutative context, or in a sub-Riemannian context, and so on. Yeah, and a lot of questions are open in that setting. In particular, a pseudo-differential calculus, a semi-classical pseudo-differential calculus, it has been more or less done on these created Lie groups. But for example, questions about wave packets or what could be an initial value representation for a sub-Laplacians, these questions they are open. Yes, that's it. I'm going to thank you for your attention. So if you have questions.
Thank you very much, Clotilde, for the interesting talk and the clear presentation. I think it interested both mathematicians and physicists. It has like both sides. So if you have questions, let us open the floor for questions if you have any.
Actually, I have a question about the Wigner function in physics. Wigner function corresponds to distribution function in classical mechanics, and I am wondering why we need the Wigner function in our study, because we are using the semi-classical expansion, but maybe we can say semi-quantum because we need the Wigner function.
Yeah, you said semi-quantum. I'm not completely at least, but maybe the underlying idea is that if you look to the Schrödinger equation, I mean, it's mixed derivations and multiplication by functions. You see, so you cannot treat directly. If you want to study directly modulus of psi epsilon of tx square, you cannot say anything about it. And but if you consider this distribution, so you are right, it's a distribution in the phase space. So we are replacing the energy density by a distribution in the phase space. We have lost the positivity of the density that we had before, but but we have this Egorov theorem which tells you that this thing is the good thing. In fact, the good thing as to associate with the wave function, it's the Wigner transform because it evolves nicely. If you look, if you want to have the evolution of the density, you need to integrate in psi. Then it will just give you modulus of psi epsilon of tx square. But if you integrate in psi here, you cannot describe this evolution nicely. In fact, it's
Okay.
So in fact, it's the intuition of quantum mechanics that the phase space is a good setting. You see, things are evolving in the phase space. The configuration space is just a projection. So when you project, you lose information, in fact.
Okay, thank you. I also have another question. In physics, we use the expectation value of operators.
Yeah.
And it's equal to observables. And I found interesting this expression, expectation value of observables. What is this?
Yeah, usually here you put what you write in physics, or what I see sometimes it's just you have a capital A with the at, you see. And so you can think that these operators are just special capital A. Yeah. Okay. So we have functions on the phase space, and with it we construct an operator, and then we do as everybody is doing, routing to A psi psi. Yeah. So it's the same. Yeah. And the point is that if you have nice A, they have you can write them like pseudos. So nice, I mean just if I don't know if they're first class, for example, you can find their symbol, their semiclassical symbol or their Lie symbol. But maybe the class is a bit restricted, but it's enough for what for getting some of the things that we wanted to see. Yeah, maybe you need more general operators for describing other things. But, yeah.
Thank you.
Is there any other question?
So can I ask a small question? Yeah. I'm wondering, how about the situation of this kind of Wigner transform in the presence of boundary? If you look at boundary value problem.
Yeah. So this is Gerd Grube is the expert. You know, at the first in the first slide, I put the name of Gerd Grube, and Gerd Grube was studying pseudodifferential calculus with boundary. But for in fact, I have never worked a lot with that, so I am not very an expert. What I know is that there is the techniques of Melrose. Melrose is when you have a boundary, they have the techniques for exposer. They add a new variable. Okay, they make a blow up of the boundary, and then they treat the boundary with this blow up. If you maybe we can discuss this if you want another day. But all these people around Melrose in the States, they use this community. When they have a boundary, they make a blow up, and then they have a machinery. So I think it's really in their paper, in this kind of papers that we can find something. Yeah. You have a special problem in mind, huh?
I'm wondering how to construct something, because to deal with boundary value problem, there are some I'm not sure how to use kind of such kind of Yukolov theory presence of boundary.
Maybe Oana, she should know Oana Ivanovici. Yeah. Yeah. But we can discuss this. Yeah.
Is there any other question? I have a question, but a bit general about the part about coherent states.
Yeah.
Because I heard the vocabulary before, coherent states, and I saw people, for example, generating, constructing operators using generated function based on the eigen functions of some noun operators or something like that. So they put the summation over or the product of eigenfunctions and construct operators based on that, which is the idea to construct a Bergman transform, I think. So in some of that. So my question is a bit general. So what's what you have presented here? What's
there is a question of terminology. So when
it's not the same thing. Okay.
Coherent states, usually when people think about coherent states, they think to something which is localized. You see, so there is you can I have take a kind of rough things because the phi is coming from nowhere. But if you look to Agathon wave packets, he is using he has some underlying harmonic oscillator, and he's using a family of eigen functions of this operator and generating a family of phi, of functions phi, which are I mean, there is, for example,
this is the same what people call wavelets. It's linked to
wavelets. No, it's not exactly the same. No, but yeah, it has some links. But yeah, no, I'm wrong. When you do wavelets, they have a frame and they decompose on the frame. It's like for the Gaussian, And what you find in the chemical literature also is that they have decompositions of the initial data on a product of wave packets, product of Gaussians, and some kind of mixed quantum classical data. Just now I talk about bon-open number approximation, which is a way to reduce dimension, but there is a lot of literature in the chemical literature today about how to reduce the dimension of a system by decomposing the data on a set of specially cooked sets of data where they use, like you say, you use eigenstates of some operator, which is more or less hidden in the initial Schrödinger operator.
Okay, thank you. Is there any other question? So there is any other questions? So let us thank again Clotilde for your talk, and thank you for all the attendees for coming. So we have another seminar in 2 weeks. So see you then. Have a good day.
Okay. Good. So, bye bye.
Okay. Thank you, Clotilde. Bye bye.
Thank you.
Bye.
Thank you, Clotilde. Thank you.
Bye.
Thanks so much.